Hey y'all, welcome back to Alakazam Math Made Easy. In the last video, we talked about related rates, which is an application of derivatives, kind of going over how we can learn something about one quantity given information about another one, right? So this video is going to be very similar because we're going to take the derivative and turn it into an application, right? But it's actually one that we've been doing since the moment we talked about tangent lines for the first time, right? The premise is that we can approximate a function as a straight line using that tangent line. So basically what we're going to do for here is we're going to build off of that and say not only can we approximate that function, but because we can do that, we're also going to be able to make a guess about that function, right? In terms of what it's doing at a different x value. So we're building it at one x value and using that constructed tangent line to approximate values other than that x that we used, right? So there's a formula for it. We'll find it's probably a little bit intuitive in nature, right? So this is going to be the construction that we use to represent that this is a linear approximation. So what we're going to do is instead of f of x, we'll call it L of x, which is the linear approximation of f of x. And then we're going to use these functions here. So here, this first chunk, f of a, is the value of the original function at the x you're using to build that, that approximation, right? F prime of a is going to serve to be the slope of your tangent line, and that's going to be plugging in the x value for the derivative. We've been doing that for a very long time. And then this last part is just x minus the value of a, right? So it's very similar to a format that you'll definitely remember. It's y minus y1 is m times x minus x1, except it's y equals y1 plus m times x minus x1. So that's essentially the exact same thing. So we've used that many times before to actually find the equation of the tangent line. We're doing basically the exact same thing here. So this example we're walking through kind of shows you how to find it, but also what we can do once we find it, right? So the first step is to find the derivative of the function that we're given, and we were given f of x is x, the cube root of x at x equals 8, right? So there's that. And then what we're going to do is we're going to find the derivative of it, but to do that, we're going to transition it from this cube root into an exponent. And if you remember, that's something we should have learned in algebra. Anytime you have an n root of a function, you can rewrite it as that function to the 1 over n. So that's a little bit of review there. But then we can take the derivative as normal. We'll take the exponent, multiply it to the front, minus 1. The rule does not change just because it's a fraction, right? So we have 1/3 x cubed because we multiplied the 1/3 to the front. Then we have 1/3 minus 3/3, or 1/3 minus 1, which gets us negative 2/3. And then basically doing this rule backwards, we get it to this form, which is easier to plug numbers into. So the next step will be to evaluate that, because remember this function needs f prime of a, which means we have to plug in the x value we're evaluating at into that function. So that's essentially exactly what we did here. We took 8 because we're asked to find it at 8, and then we plugged it into the function we got here, which led us to 1/12. And then the next step, that's going to be our m, right, in our equation. And then this next step is to find the value of the original function by plugging 8 into the original function. And that's going to give us 2. So that's going to be our f of a, or what we're going to call, or well, our y1, or what we call f of a. This is going to be m, or f prime of a. Right, so then what we're going to do is we're going to plug those values into the linear approximation formula, and we get this to be our answer, right? So what good does it do us in this form? Not a lot. Basically, we just found the equation of the tangent line. That's not anything new from what we've been doing. What we can do now, though, is use that linear equation to approximate different x values on that function. So here I find one a little bit higher than 8. Here I find one a little bit lower than 8. And here's one that ends up being way further down the line. And we'll see why that's not necessarily a good idea in a second, right? So the actual value of this function, like if I were to take the cube root of 8.1, I get 2.008299. And if I use our linear approximation, I get 2.008333. So it's a little bit off, but very, very, very little bit, right? Same thing with 7.9. It's a very similar number, 1.9916317 to 1.991667, right? So those are very, very close, which means that this linear approximation we found is very accurate for values close to 8. Now, what happens if I plug in 32? Right, if I plug in 32, I get a number. So if I plug in 32 into the actual equation, I get 3.174802, right? But if I plug 32 into our linear approximation, I get 4. So you'll notice that the further you get from 8, the less accurate your linear approximation is. And that makes sense because the function's not linear, so it won't consistently be an accurate representation of the system. So real quick, let's summarize a couple of the benefits and detriments or limitations of the linear approximation method, right? So what we'll do is start with pros, right? So with the linear approximation method, you end up having to do less rigorous math than plugging it in. In the example above where it was just cube root of x, that's not necessarily 100% the case. But when it's super more complicated, where it's a super complicated function, that's not always going to be as easy to just plug and chug, right? So sometimes a linear representation of that function in the surrounding area is much easier to evaluate. Same thing, it's very accurate to do so when you're looking at numbers close to the one that you used, right? So we used a equals 8 to form the line, right? We were given a equals 8. And when we were looking at 8.1, 7.9, these things, those were relatively accurate representations, right? So what are some drawbacks, right? If I need to find, it's not an all-encompassing function, right? So I can't use this linear approximation that I found and find any number on the function, right? It's going to get less and less accurate as I get further from x. So that's this one. It gets less accurate at far distances. But what that means is if I want to find several values of the function approximately, I'm going to need to do several linear approximations, right? So at some point, there's a trade-off between these two, right? If I have to keep finding new linear approximations, it might be better off, or my time might be better spent just plugging it in and finding the actual value, even though it might be more computationally intense than just one, right? But if I need to find just one, approximation and find numerical values for neighboring, quantities, it would definitely be easier to find the linear approximation. So this was one application of derivatives. It's something that we've been doing for a while. I do want to highlight again the fact that you don't necessarily need to remember a new equation, right? This is written in a different format, this one, but it's the same equation we've been using the whole time. The reason why it's written this way is because sometimes it's easier to remember which function to plug into. But if you can remember conceptually that y is just the variable, right? That's what we're setting it equal to. That'll be L of x. That's what we're looking for. This is asking for the y value of the original function. So you plug a into the original function. This term is asking you for the slope of the original function, right? Which we find with the derivative, and you still plug it in because you need a number, not an equation. And then this term is just the x value this term is just the x value we are evaluating at which is given, right? So it's the same function. You don't necessarily have to remember something new, but it's kind of helpful if you don't necessarily feel 100% comfortable with applications of that specific function yet. So that is linear approximations. If you have questions, leave them in the comments of the video. If you've learned something from this video, give it a like. If you want to keep up to date with my new content as I post it, feel free to subscribe to my channel and turn on notifications so you get updated when I update new videos. And as always, best of luck.